before, during, and after implementation logistics, and then a few recommendations and lessons learned. Okay, so what is ISCO? And I really appreciate a lot of slides, all slides, and introducing this so that I don't have to dwell into redox reactions. But the bottom line is you always have an electron donor and an electron acceptor. When you're talking about an oxidation, the contaminant is actually the electron donor. And what you're doing is you're adding a massive a massive supply of thermodynamically powerful electron acceptors. And that's what the oxidants are, okay? One of the things that's unique about ISCO, though, is that you can create a secondary reductive pathway. And I'll talk about the chemistry in a little bit, several slides down the road. But the mechanism is actually usually that you're oxidizing water, okay? And as you're oxidizing water, you can actually form this compound called superoxide, and it's a reductant, okay? So you can basically, though, the takeaway is massive supply of thermodynamically powerful electron acceptors. The thermodynamically powerful just means it will treat with a lot of things, treat a lot of different contaminants, so it will react with a lot of different things. Okay, so why ISCO? First of all, it's effective. It's, we've been at this, really since the dawn of ISCO, 40 years. We know a lot of different contaminants that have been effectively treated in the subsurface. We have a lot of bench test data for some other contaminants. We know that it is an effective technology for many contaminants of concern. It wouldn't be around after 20 years of persulfates, 40 years of hydrogen peroxide. It wouldn't be around if it was not the cost-effective remedy. That is what the feasibility studies are often trying to determine, is which technology is most cost-effective, and quite often it is ISCO. Time. This is actually one of the big differentiators of ISCO versus a number of the other technologies. It tends to be fast-acting. So if you are doing a redevelopment project and you want to, be building a skyscraper or be working on a condominium within 6 months or 9 months or a year, something that is going to be relatively quickly, ISCO can provide you remedy and a time to confirm that effectiveness within that time frame. So it tends to be a very fast-acting technology. You can slow it down when you want to slow it down. There are ways of doing that. We'll talk about that a little bit. But time is a big factor and a characteristic. And when you want fast results, ISCO is one of the technologies that can help give you those results quickly. Flexible. Because you can dissolve reagents or apply it as a dissolved reagent, solid slurry, you can control the concentrations and the masses that you're injecting. Because there are all different types of ISCO, it's actually a fairly flexible technology. It can be used in permeable reactive barriers. It can be used to go after source zones. It can be used to go after plumes. It really is a fairly flexible technology once you understand the fundamentals of how each of the different ISCO technologies work. And contaminant mass. It has a nice range, several order of magnitude range of contaminant mass that I would refer to as its sweet spot. Again, because you can dissolve a large amount of these electron acceptors into the aqueous phase and distribute. You can be applying a lot of ISCO to go after a lot of contamination. And then ease, because we've been at this for so long, there is just this industry-wide level of expertise. You can find labs that know how to monitor for ISCO, labs that will do bench studies, contractors that have applied ISCO, consultants that have worked with ISCO. There have been, large consultancies that have ISCO experts within the consultancy. So there is this, worldwide level of expertise that has developed in applying ISCO, and experience is very critical in making sure that you can apply technology successfully. So, common oxidants. I don't spend much time talking about each oxidant. I have some specific slides. So this is the first one. Hydrogen peroxide is the granddaddy of them all. People were in the 1980s going out using hydrogen peroxide to try to remediate sites. It can degrade. You split it, you activate it, catalyze it, you then form the hydroxyl radical, which is an oxidant, and superoxide radical anion, which is the reductant. You have persulfate, which can be two salts that are used in our industry, sodium and potassium persulfate. The main difference is solubility. They both dissolve to give you the sulfate anion, which is the source of the oxidation potential. It can be activated to form hydroxyl radical, an oxidant, sulfate radical, another oxidant, and the superoxide radical anion with the right activation. Permanganate, no radicals, okay? It is direct oxidation, so it's a different mechanism. That's one of the first things really to be paying attention to here. Up above, I was talking about radicals. Radicals react very quickly, and they're the ones doing most of the heavy lifting, the work. Permanganate, it's doing the work itself, but it's direct oxidation going slowly, no reductive pathway. Ozone, a little bit more complicated. It can be under a certain pH conditions, it can be an oxidant only, but you get above pH 9, 9.5, and then you can start getting the radicals. So it can actually do both. So the selection process. So Paul was making a joke because we each have our different lists that we work off of. And I will say, and this is a big assumption, after you've gone through the steps that are necessary, so many steps in our industry, but after you've gone through the steps where you understand your remediation goals and you understand your remediation timeframe, you have a good idea of what you're actually trying to accomplish at the site. I'm making the assumption that that's already happened. Not always the case. Making that assumption. That you understand the site, you understand the soil characteristics, you understand the groundwater characteristics, you understand the limitations of the site. Again, that's a lot of effort that goes into that. And then the contaminant characteristics. And this is actually something that I think is underappreciated in our industry. The contaminants have characteristics. They have different solubilities. They have different retardation coefficients. They have different KOCs. And some things, for example, if you're dealing with a petroleum hydrocarbon site, you could have a BTEX that has a KOC of 54 or something like that, and a pH that has a KOC that is several hundred, if not several thousand. Those are going to behave differently. They're going to be treated differently. So understanding the contaminant characteristics. Once you've done all of that, here's the process that I kind of go through. And what I'm trying to get to is technical efficacy. Will ISCO or will bioremediation or some other technology work? And I like to make it simple, yes or no. It's binary. Will it work, yes or no? Then you can move on. Next is kinetics. And this is where, remediation time frame becomes important. What you're trying to accomplish becomes important. But what are the kinetics? How quickly does it happen? Will it work in the time frame that you want it to work? Can you maintain that contact time? If you need a week of contact time, or if you need 3 months of contact time, can you actually maintain that contact time in the subsurface? Application method, okay? Have a slide. I'm sure you guys have all heard it, but this is a contact sport, okay? And I actually take it beyond just establishing contact. You have to maintain contact with a sufficient amount of oxidant in order to achieve your goals and treat your contaminants. So application method is how we do that. Critical, okay? Absolutely critical. The other thing, just to work into the whole process, the massive applications, number of applications, and how it affects cost, because of course, total cost is the driver at so many sites. Okay, reagents have characteristics too. Contaminants have characteristics, application methods have characteristics, reagents have characteristics. One of the jobs that we're trying to do is match them all together so that people can be successful at their site. Let's switch this up for some reason. It was driving me nuts holding this in my left hand. So thermodynamics, reactivity with the contaminants. Okay, this gives free energy. You can go in and you can calculate this. A lot of people rely on studies. They like to see it's worked at least in the laboratory. Cool. But thermodynamics, yes or no? Will it work? Yes or no? Kinetics, the rate of reaction with the contaminants, very relevant. Okay. Some contaminants degrade very quickly. Some contaminants degrade very slowly. Even with some of the radicals, some things like MTBE, just so you know, it takes a while with MTBE. Other things, 1,4-dioxane, very quick. The kinetics does come into play. Persistence, okay? So how long will the reagent be active in your site? This gets down to what's the solubility, what's the stability of the reagent. We're going to talk about this in a second, but hydrogen peroxide reacts very quickly, can be very unstable. Persulfate tends to last longer, permanganate tends to last longer. These are all characteristics of the oxidant. Mass per application, this gets down to solubility, how you're applying it. Is it a solid slurry? Is it being soil mixed in? These types of things. And then things like color. Permanganate, one of the things people don't like about permanganate is its color, okay? Some people like the color, okay? It really gets down to what you like, what you're trying to do at a site. And, the famous thing with permanganate is, somehow it hit a utility out there in San Francisco, Hunter's Point, and it got to the bay. That didn't make people happy, having purple bay out there, okay? So color can matter. I know rivers that have turned purple because of permanganate. Color can matter. Okay, so starting off with these different categories and working our way through them. Technical efficacy, yes or no? Again, the oxidative pathway, reductive pathway have been talked about, but generally speaking, both are always going on. Something's the electron donor, something's the electron acceptor. When you say it's an oxidative pathway, it means that you're supplying the electron acceptor, and you're usually treating the contaminant as the electron donor. Reductive pathway, vice versa. One of the things I just wanted to point out, though, this is how you can, get the reductive pathway in ISCO, because some people, I think most people generally accepted it. We've treated enough carbon tetrachloride that most people do kind of understand it. This is one of the mechanisms. There's actually a couple of different mechanisms. But like I said, you're oxidizing water. And it's one of those things with water, you got to stop thinking of it as inert. It's actually, not only is it an important reagent because everything happens in the aqueous phase, but most of these oxidants are capable of oxidizing water. Okay, and here's persulfate reacting with water, and this is the hydroperoxide, which is a nucleophile, but this is actually the conjugate base of hydrogen peroxide. You add one more hydrogen there, and you get hydrogen peroxide, but this is under alkene conditions. So under alkene conditions, it's deprotonated like that, okay? Then you oxidize hydrogen peroxide with persulfate here, and you get the sulfate radical, and there's your superoxide. So that's how you can get an oxidative pathway and a reductive pathway out of the same reaction. You're oxidizing water. Now, the other way to visualize that is oxygen goes to water. Water is reduced oxygen. In between the two of those is hydrogen peroxide. So you do oxygen, 2 electron transfer, hydrogen peroxide, 2 electron transfer, you get water, okay? In between hydrogen peroxide and oxygen is superoxide. And so as you go through that little spectrum, as you're oxidizing water to oxygen, you go through superoxide. That's the other way to kind of visualize it. Okay, thermodynamics. Why are these radicals so important, and why do people get so excited about them, including me? They are some of the most powerful, thermodynamically powerful reagents out there, okay? There's very few things. There's like 3 things that we know of that have a higher standard reduction potential than the hydroxyl radical and sulfate radical. What that really means is they're capable of reacting with most things. There are things that they won't react with. Okay, there's not enough energy because, in a way, this is a measure of the energy that these things react with. There are a few things that they don't react with. So, they're out there. PFOS, okay, doesn't react. PFCAs do react. Okay, so, even within PFOS, it gets kind of interesting. But just working our way down, you can kind of see, okay, so you activate persulfate right there, strong enough oxidant on its own, but you can get stronger oxidants with the hydroxyl radical and the sulfate radical. But, you go through and you oxidize water, and there's superoxide, which is lower than hydrogen, which is, bioremediation, approaching the reduction potential of 0-valent iron. So it's a legit reductant, okay? It will react with, reduce close to as many things as 0-valent iron, and it'll reduce more things than you can do biotically, typically. So again, going through the compounds, hydrogen peroxide, you get both. You can get hydroxyl radical and you get superoxide. The persulfate, you can get, all 3. Permanganate, direct oxidation, and ozone, it depends on pH. So what does this mean? What does this practically mean? It means that different ISCO compounds or different ISCO reagents can react with and treat different contaminants. Sometimes, so oxidative things that were, typically things that are reduced will be treated oxidatively. So petroleum hydrocarbons, MGP residuals, BTEX, PHs, oxygenates, 1,4-dioxane, things like that. Those things are typically reduced, so they can be treated oxidatively. Then you have things that are completely oxidized. They tend to be treated reductively, okay? Carbon tetrachloride, 1,1,1-TCA, DCAs, the chlorinated ethanes, a few other things need the reductive pathway. Then there's a group of compounds that are treated by either. Now, they're treated by either, it's actually different mechanisms. And just to point that out with PCE, the chlorinated ethanes, if you're doing them reductively, it's typically reductive dechlorination, where you're donating an electron, the electron's donated to chloride, the chloride pops off, okay? With ISCO, they tend to go after the double bond, okay? And that's why the chlorinated ethanes don't react oxidatively, but the chlorinated ethenes do react oxidatively as you're going after the double bond. That double bond is called a pi bond. And it actually, if you remember those little stick figures we played with in chemistry, it's the little bond that sticks up really high. Oxidants are also called electrophiles, and it's going after the electron there, okay? So with persulfate, activation matters. So hydrogen peroxide, your Fenton's reagents, they give you, because you get superoxide and the hydroxyl radical, you can go across the spectrum. Alkaline or hydrogen peroxide activated persulfate, you can go across the spectrum. You start talking about activation of activated persulfate iron chelate, you're only talking about oxidative pathway only, okay? Because it doesn't oxidize water in this instance, not fast enough anyways to be really significant. Permanganate, oxidative pathway only, and it's dashed because it's actually not all of these, and we'll talk about this on the next slide. Ozone, it depends what pH are you at. Under, less than alkaline conditions, it's going to give you the oxidative pathway. It's a very powerful oxidant. It is going to treat your hydrocarbons. But if you get above pH 9.5 or so, you can actually get some of these compounds that only go reductively. Okay, so I like to make things simple. It's easy. It makes communication easier. But yes or no, and sometimes, and maybe. Okay, so that's where we're at with permanganate. Okay, so permanganate is, thermodynamically a powerful oxidant. It reacts with a lot of things vigorously, but you have to understand kinetics. Okay, and this is kind of almost a segue as I start talking about kinetics. You think about the other technologies, what you're doing like with a persulfate or a hydrogen peroxide is you're taking the parent compound and you're trying to push it out into the subsurface. So the stability of the parent compound is paramount to distribution. Then you activate it in close proximity to the contaminant, and it reacts with the contaminant. Permanganate, there's not that activation step. It's just you're pushing out the parent compound. There's a direct oxidation, so the thing that limits it is actually its rate of reaction. And so typically most people think and associate permanganate with treatment of chlorinated ethenes. And if you look at TCE and PCE and you look at this 10,000 ppm or 10 gram per liter, your half-life is 1 minute, okay? So if you establish contact between 10 gram per liter permanganate with PCE for 1 minute, you get 50% reduction. 99% treatment is 7 half-lives. So if you can maintain contact for 7 minutes in the half-life in the subsurface, you're going to get greater than 99% treatment. This is great, okay? This is why people associate treatment of chlorinated ethenes with permanganate. Now, some people say that it'll treat TECs, right? The toluene, xylene, ethyl benzenes. And you can kind of see, so going up a little bit higher, I'll just pick on, like right in there, xylenes, toluenes, it's 1 day half-life. So if you can maintain contact of 10 gram per liter for a week, then you can get greater than 99% treatment of these compounds. But you talk about benzene, that's a year, okay? Half-life, 10 gram per liter, that's a year. Are you gonna go out there with permanganate, maintain contact with benzene for 7 years? It's not gonna happen. You're not gonna want to monitor it for that long. And so all of a sudden when you're trying to treat benzene, not that it can't, thermodynamically it can, it's just it's kinetically very slow. And then the other thing is just to start looking at concentrations. Are you going to actually maintain 10 gram per liter with an application, or is it going to be 1,000, or is it going to be 100? And then all of a sudden you can see why, even with PCE, that's still pretty effective. Say that's, looking at the 1 day mark, even if you do, 1/10 of a gram per liter, you can get PCE in, I'll just call it the 1 day. You're still looking at less than a week to treat PCE of contact time, even at a more dilute concentration. But like one of the things that happens is, there's those studies out there talking about how 1,4-dioxane is commingled with PCE at, like over half the sites. 1,4-dioxane, are there studies out there showing it can be treated? Yes. Can it be treated? Sure. Are you going to maintain, so that's a 1 month contact time at 10 grams per liter. Are you going to maintain contact with between 1,4-dioxane and 10 grams per liter of permanganate for 7 months? And those are the questions you have to be asking yourself. Is that achievable or not? Kinetics, longevity, talk about this. So I like I said, one of my overarching themes of this presentation is matching up what you're trying to do, what your remedial goals are, your remediation time frame, and the oxidants, okay? And this applies to bio, this applies to ISCO. Even if you're talking about bio, you want a fast-acting, reductant lactate. If you want something that's slower, hey, lecithin or oils, those that react slower. Within the realm of ISCO, hydrogen peroxide tends to react very quickly. Sodium persulfate and sodium permanganate, it's in the weeks to months range. But if you want something that persists longer, you can have potassium persulfate and potassium permanganate, inject them at above their solubility limits, and they're going to sit there. And we've had sites where potassium persulfate was observed for up to 3 years, and that's how you can get much longer. An oxidant that's persisting for much longer is you have to look at something like that. But one of my points here is whether or not you're talking about bioremediation or ISCO, there are these mechanisms to longevity, like with sodium persulfate or potassium persulfate, potassium permanganate. It's a low solubility, right? So you look at the solubility and inject it above that solubility. With something like these buttons are so close. Okay, if you look at something like an organic electron donor that is going to last years, the oils, the lecithin, it's a fermentation process. Okay, And that's the process that slowly takes those larger molecules and breaks them down to fatty acid, which eventually goes to hydrogen and all of those things and all those mechanisms. So there's basically, you're adding the reagent and there's a mechanism that helps it persist for longer. And other things are readily available, like the lactate or the hydrogen peroxide or the, folate aqueous persulfates and permanganate. So how do we start matching these up? You guys are going to have, it's going to be site specific. You're going to know, you're probably thinking about sites right now. But really, you tend to want things that react quickly and are available very quickly to go after source zones, high oxidant demand concentrations, high contaminant concentrations, things like that. Okay, that you want to go in there, you want to hit those hard, you want to hit those quickly. You have a redevelopment site, you want something available right away to do whatever damage it's going to do very quickly. Extended release, permeable reactive barriers. Paul's going to be talking about back diffusion from low permeable soils. Okay, there's a physical process, back diffusion out of something that's less permeable. You can have an oxidant that's going to be sitting there reacting. Low solubility contaminants, high KOC contaminants, low contaminant concentrations, and even high groundwater velocities. All of these things are times when people have been using these lower solubility oxidants. To use this as an example, here's some PCBs. This was 1254. And you can see sodium persulfate, even at 56 days, you're seeing that potassium persulfate outperformed. This is a bench study, sodium persulfate, because it was sitting there persisting longer. So PCBs, low solubility, high KOC, it's sorbed to soil. I know people ask me all the time, can you treat PCBs? The answer is yes. Thermodynamically, yeah, they react very quickly in the aqueous phase. It's getting them to the aqueous phase. The diffusion, the desorption, that's the limiting step. So you need to have an oxidant or an oxidant strategy that is going to allow your oxidant to be there when the PCBs desorb off the soils. So characteristics, oxidants. Hydrogen peroxide, great technology. That's my PhD was in. I've applied hydrogen peroxide all over New Hampshire, actually. It's got a fatal flaw. The reason why it hasn't, it's almost perfect remedial technology, in my opinion. Did decompose to form oxygen in the water. How great is that? Very low residuals. The issue is that hydrogen peroxide sits between oxygen and water. All you need is an electron shuttle, and it will react with itself. It's called auto decomposition. It'll react with itself and decompose to oxygen and water. Well, what are transition metals? Manganese, copper, iron, any transition metal. Where are transition metals? Soil. Where are contaminants? Soil. So I used to run the laboratory company in Stroud, New Hampshire called XTD. Not there anymore. They're LEA now. But I was the lab director for a long time, and we would run a number of month studies. And I have had sites where the half-life of hydrogen peroxide was 4 minutes. You're not going to get much distribution from an injection well with a half-life of 4 minutes. It was decomposing form gases that quickly, almost explosive. Okay. I've also had sites, these folks were from Long Island, where the half-life was in weeks. So that's the trick. That's the trick to making hydrogen peroxide work. If you can get a half-life long enough that it will be persistent to distribute that parent molecule out into the formation and have it persist, hydrogen peroxide is a great technology. Okay, permanganate. Okay, so I actually got into a little bit of a fight with some people when I was forming this slide for another presentation, and they maintain that there is an auto decomposition mechanism. I maintain that there wasn't. I've never seen it. So we compromise on it was very, very, very slow auto decomposition. Okay, so it's negligible. It is about the best way I put it. Persulfate, yes, persulfate oxidizes water. It oxidizes water faster under alkaline conditions. Why? There is a reductive pathway, a reasonable reductive pathway at high pH, because that oxidation of water is faster at high pH. Under acidic conditions, pH is logarithmic, right? So as you move away from high pH conditions, your kinetics are slowing down by orders of magnitude. So by the time you get to a neutral pH, instead of pH of say 11, that's 4 orders of magnitude. So what was reasonable, maybe, decomposition rates around 1 month. All of a sudden you're talking about, 4 orders of magnitude to 10,000 months. There's an auto decomposition pathway. It's really slow. So pH matters, with persulfate. Under alkaline conditions, it's faster. Under acidic conditions, it's painfully slow. Ozone auto decomposition very fast, which is the problem here, right? Because of the reaction with transition metals, hydrogen peroxide's persistence, typical persistence is minutes to days. Permanganate is actually so slow. A lot of people actually underdose permanganate because they don't want the site to stay purple. Okay. And that was a problem. There's actually some studies, and there's some early 2000s when people were playing around and figuring out permanganate. There was these presentations, and by the way, 3 years later, our site's still purple. And yeah, it's a bit of an issue with the permanganate. Persulfate, typically, once dissolved, persulfate anion will actually persist for weeks to months. We say 2 to 8 weeks is kind of typical because there is that auto decomposition pathway. It also will react because it's a peroxygen, like hydrogen peroxide. The transition metals, and this is why it doesn't last 10,000 months in the subsurface. It will last because the transition metals typically, weeks to months. So very slow auto decomposition, but it does decompose. Ozone, and this is one of the two problems with ozone, or one of the issues that you really have to pay attention to. Well, in water, ozone will decompose in minutes. In the gas phase, ozone will decompose in days. So that's actually why everybody, when they're doing ozone, they try to distribute the gas. They try to get the gas up in formation, and then the ozone, diffuses out of the gas into the water, and that's where it reacts with the contaminant. But even with that, you only have persistence in the range of days. So how much gas can you get out into formation? That's a big limiting factor with ozone. Okay, just real quickly, just like to actually talk about site data, just not theoretical data. This stuff does work. This as an example. This is a KP PRB that was done in upstate New York. Just to talk about the different pathways, this was alkaline activated persulfate. DCA needs the reductive pathway. DCE can go via either pathway. 1,4-dioxane needs the oxidative pathway. And what you can see is from baseline to 3 months. So here's a KP, so persistent for 6 months or longer. And you see basically non-detect, right, inside the PRB. So it's 3 feet down gradient of the injection line. We had also, this was a pilot test, we also had a monitoring well about 10 feet down gradient. And you see about 86 and 82% reduction, still very good. And you're seeing, and you're actually seeing exactly what you'd expect. The oxidative pathway, you're getting some NDs here and here. You're getting better treatment of the 1,4-dioxane and DCE because the oxidative pathway and the reductive pathway both are going on and can treat those. But the DCA that needs the reductive conditions, the alkalinity that doesn't migrate very far outside the PRB, even if the persulfate was, so you don't get as good a treatment as the DCA, but you were getting it move further down gradient, 6 months transit time, and you're seeing 65, 62% reduction. And again, less treatment, preferential treatment of the DCAs, and you saw some better treatment of the other compounds. Okay, application methods. Okay, the mantra. I don't care if you're talking about ISCO or bio or precipitation. These are contact sports. You have to figure out how to establish contact. And I think it's beyond just establishing contact. You have to establish contact, maintain contact, and a sufficient mass of the reagents. Okay. And again, I'm talking about ozone. Thermodynamically, it works, but can you get enough mass out to where you want it to get? Okay. So these are the keys to making these technologies work, and application methods are absolutely critical. Injection strategies are really, kind of the granddaddy of the application methods. Two most common are injection through injection wells, 10-slot screen, going out there, fixed wells, a DPT, recirculation, and this is where matching reagent with application strategy comes in. If you're going through one of those, you don't want to be injecting a solid slurry. I don't care if the solid slurry is smaller than the 10-slot, which tends to be about 500 and I think it's 30 microns. Like closure SP or closure KP is actually around 50 to 80 microns. I still will not tell you to inject it through a 10-slot screen because of bridging. Okay, you get too many particles ramming together. It's like everybody trying to hit the exit. After somebody pulls the fire alarm, sure, one person at a time can go through the exit, but bunch everybody up, and it's mayhem. So when you start talking about solid reagents, you tend to need something else, and it tends to be TAM tubes, something that's done in Europe very commonly. In North America, not so much. TAM tubes, but they're basically solid tubes with little ports with a rubber gasket on the outside of them. DPT is what most people in North America do, but it's high pressure solid slurry injection, and you're basically fracturing the subsurface and pushing fractures out there. So less intrusive to site activities, low footprint. You don't need access to the surface as much as you do with the other main technology that's out there, soil mixing. But there are some serious advantages to soil mixing, and so I'm glad more and more people are doing it. By the way, this is a site in New Hampshire. Those of you, some of you might be familiar. Okay, liquid injection via fixed soils, fully soluble reagents only. That's what we recommend. Recommend for permeable soils. It can work with low perm soils. One of the things I say with low perm soils is you got to think the contaminant got in there, and however the contaminant got in there, you can probably get some of the reagent in there. The issue gets to be diffusion. So like if there's a sand stringer or a fracture in the clay, you can usually get your reagents through an injection strategy to go along the same things. I've seen 80, 90% treatment, but then I've never seen really better than that, just because, the contaminant also had time to diffuse out, and the oxidants just don't have that same decades amount of time to do that diffusion. The other big key takeaway, I'm trying to get people to think about the reagent solution, not just as a way to get the mass in the ground, but as the way to distribute the reagent, okay? Kind of one of the classics is you can have a 10-foot ROI, and then people go out there and they inject, like 50 gallons. And it's just like, you treated, 6 inches from your well really well, but you didn't go out 10 foot, okay? So one of the things, and just to, give you an idea, we're recommending thinking about it in terms of effective porosity, and we're encouraging people to inject 50 to 100% of the effective porosity. And that's your ROI. Specialized fracturing, solid reagents, potassium permanganate, potassium persulfate, calcium peroxide. Haven't really been talking about it, but it's more oxygen release. You can see what it looks like. Here's a fracture, that's about 1 centimeter thick. Here's the permanganate, great visual. I said it was purple. There's what it looks like. And that's a little less than 1 centimeter, so probably a little bit further out in the fracture. But you can see how it's diffusing out into the sand formation. I call these pancakes. A lot of my analogies are food-based. Don't know why, don't judge me. Okay, but you can see these pancakes going out, and this is the theory of how it works, is that you do these fractures and they push it out. And basically then you get diffusion. One of two things happens. If groundwater is moving through, it goes through the fracture, it goes through the zone where things are diffusing into. Or of course, if you're doing a source zone treatment, you basically want to stage your fractures so that you can diffuse out, and from the fracture, treat the soils in between the two different fractures. In-situ soil mixing, becoming more popular for a simple reason: cost. It's becoming more prevalent, okay? Back in the 2000s, in-situ soil mixing the mobilization cost of the tooling was almost too expensive to go up. But because of the, and so when you did it, it would be something just like with an excavator bucket, which isn't the best, okay? But with the advent of, this is the Bill Lang mixer, and some people have bought mixers off of Bill, so other consultants have these kind of mixers. There's also the Alu soil mixers. But then these guys are becoming much more prevalent. There's all sorts of groups: GeoSolutions, NTAC, what's the one down in Texas, Recon, and there's a couple out in California. A lot of people now have these and can mobilize them more cost effectively than they used to. There's some huge advantages of soil mixing, and it really gets down to two things, three things. One, they homogenize everything. Okay, so if your contaminants are spread apart unevenly, this blends it all together, so it homogenizes the contaminant. If you have little stringers of napple, those stringers get blended together in soil, and you can better establish contact with them. It also takes the oxidant. Instead of an oxidant going through an injection and following preferential flow paths, soil mixing doesn't care about preferential flow paths. It's mixing it all together. Okay, so you homogenize, if you think about it, the results that you saw in the bench basically was soil mixing. They just did it with a little spoon, mixed it all together in the bench. So if you're getting 99% treatment in the bench, this is the closest thing that you can do to achieve that same kind of establishing contact in the field. One of the other big things about soil mixing, if you think about an injection strategy, you're limited by the injection volume you can get into the ground, which means you're limited by the solubility of the reagent in that solution. Okay, you tend to be able to get about 1 to 3% by weight soil of oxidant into the ground. With soil mixing, you can kind of get whatever you want. Okay, 0.5 to 5% is typical. We go up to 10%. If you want to go above 10%, give me a call. We have seen exciting things. These are oxidants. These react with things. Actually, it was my birthday down in Florida. I was on vacation, get a call, job in Sweden, and they were just like, it's on fire. I'm like, what's on fire? They applied water, it worked, okay? But, in that instance, and this is one of those things, being out in the field, you got to make good judgments. They underdosed one portion of the site, so they decided to overdose another portion of the site. And it was an alveolar zone, so they didn't have much water. So I still to this day don't know how much oxidant they applied, but it was a lot. And they were in a alveolar zone. And one of the other things about that site is they had been surprised by how much naphtha they had. And it was a petroleum hydrocarbon site. So yeah, gas, you have a fire triangle. You have your oxidant, you got some heat going, and you had copious amounts of fuel. So, but less than 10%, never seen that problem, okay? That problem tends to creep up, it seems, around 15, 20%. The other issue here is that you can combine all these things with ISS, in-situ solidification stabilization. So what's that? It's this, okay? It's making this. So it's basically adding a binder, Portland cement, usually blast furnace slag, often mix in, love the combination of the two. You mix them together, and basically the alkalinity from the Portland cement creates alkaline activated persulfate. You don't need any other alkaline activator. Portland cement is enough, okay? That creates a cost-effective alkaline activation method. You blend them together, soil mix, you establish great contact, you get your treatment, and we tend to see pretty good treatment. So you establish contact, it's can get as much mass in the ground, and then you walk away, and this is what it looks like, okay? Two great things about that. One, if you're redeveloping a site, you can go out and they can put their big tools on that and they can redevelop the site, okay? They can, but the thing is, it's not concrete, okay? Concrete, 3,000, 8,000 PSI. Target is usually around 20 to maybe 60 PSI. This is not concrete. It's more of a super stiff, low permeable clay. So, and that's the second benefit of this. So you can go out, you can redevelop it, but also any residual contamination is bound up in that matrix. It's low permeable, and so your mass flux coming out of that is going to be unlikely. Most of the sites that we're dealing with that are doing ISCO ISS, they have goals like vapor intrusion because it's going to impede leachate, it's going to impede vapor intrusion, and they want to do some sort of, they want to have some sort of structural integrity after an ISCO application, like putting a road on it, like putting a building on it, which is what Stockholm was doing. So this is a big Stockholm job. We've been presenting on it a couple of times. It's actually got multiple different components. This is the component that was ISCO ISS. It's a clay lens. Underneath is a highly permeable lens. It's glacial out of wash, but they have clay on top of it. So they were rerouting the road, and they want to build condominiums on this former MGP site. And so the clay, highly contaminated with different kinds of MGP residuals, soil mixed it, and they've prepped the condominiums, haven't started building them, but they have rerouted the road. The road is sitting on this. So large 50,000 cubic meters. It was hit with about 1.8% weight sodium sulfate, with about 4 to 8% weight slag cement, so blast furnace slag and Portland cement. And you can see within 1.5 weeks, they had achieved the remedial goals. So, and you see a slightly different shift in the mix of this, but overall 95% reduction of the small pHs, 90% reduction of the medium, and 80% of the heavy. You do get a little bit, again, things that are soluble. That's what we treat. You got to diffuse. You got to get off the soil and into the aqueous phase for the ISCO to react with them. And you can see that there. And basically all samples they collected were below their remedial goal of 250 milligram, which was a vapor intrusion derived number. So understanding oxidants, again, just trying to get through. Liquid injection, hydrogen peroxide, it's all liquid. There's no solid slurry with hydrogen peroxide. I tend to limit it to 10%. For those of you that have been around as long as me, some people used to apply more than that. People have launched wells out of the ground because, about for every gallon of about 6 to 10% hydrogen peroxide, you're getting 10 gallons of gas. And you got to think about where it's going to go, okay? It can get very exciting. It's actually a job in New Hampshire where I coined the term geysers are good because it shows where things are distributing, okay? But it's exciting. I don't necessarily always need that level of excitement in my life. Permanganate, potassium, again, salt matters. Potassium permanganate, 30 grams per liter. That's temperature dependent. It really can get up to 60 or 80 in higher temps, but we're not in Florida here. In application temperatures up here in New Hampshire in the Northwest, it's really going to be about 30 grams per liter that it will dissolve that. Sodium permanganate, it's actually up to 40% by weight, but most people apply it or even deliver it to the site at lower concentrations. We recommend for sodium persulfate 50 to 250 grams per liter. And then ozone, this is the other thing about ozone. It's limited by the mass that you can get into the mass of gas that you can get into the ground, and then the mass and the percent of ozone that is in those bubbles. Because most ozone is made by on-site generators, and it's usually like 3% ozone that you're injecting. And then the subsurface can only take so much gas. So there's, liquid injection but there's one of the other limitations with ozone. Solid slurry injections with potassium permanganate, potassium persulfate, usually you're limited by 1 to 1.5% by weight, and that's kind of pushing it. That could get exciting. Out there in the field, 0.5% to 1%, probably a little bit better. Depends on if you're a sand, nice sand, or a clay, so think about those things. Soil mixing, hydroperoxide, limited by heat and gas evolution, it is done, but it can get interesting. Permanganate, high concentrations, really, you know, I don't know what the upper limit would be for permanganate. With persulfate, high concentrations, but we tend to limit it to 10% is what we advise. Permeable reactive barriers, hydroperoxide, people do it. Continuous injection of the, you know, other oxidants or the potassium salts. You know, again, we've seen potassium persulfate out there for 3 years. Ozone sparge system, this is actually one of the areas where I like ozone, okay? There's a couple sites that I know of where people put in an ozone sparge system in a nice conductive sandy soil, and guess what? They, you know, it's one of those things, everything fits. Persistence of days, great. You know, under you know, getting a nice oxidative pathway, great. There's an MGP site. The site that I tend to think about is MGP site on Long Island. And it's kind of funny because the whole site's being remediated because a bunch of rich guys' boats were getting cold car bubbles on them. And so that's no good. So basically they decided that source zone treatment was going to be a little bit expensive. And so they created 3 barriers. The first barrier was an ozone biosparge system, and then there were 2 oxygen biosparge systems. And now the boat owners are happy. Okay. Favorable versus unfavorable. Okay. I don't know if you guys know who these gentlemen are, but they are world-renowned investors. They are the brains behind Berkshire Hathaway, okay, which is a multiple billion, it's approaching $1 trillion net worth company. You see their realty signs, Berkshire Hathaway out. That's actually, they bought Berkshire Hathaway and they just adopted the name back in the day. Most people know Warren Buffett, the gentleman on the right here. But Warren even credits his success to the guy on the left. His name is Charlie Munger. Okay, I actually, you know, I like money too. One of my degrees was economics. And so listening to these guys actually fascinates me. And listening to Charlie, he's got a lot of theories, and they've both been very generous with what they talk about and how they've had success. If you go out onto YouTube or if you read some of the books out there, one of Charlie's quotes is to invert, always invert. So when I was tasked with what are the favorable conditions for ISCO, this is actually what I thought about, that quote, invert, always invert. In World War II, he was, it was stateside, I think it was Nebraska. He was a weather forecaster for an Air Force site. And, you know, so he started looking at that, and he cites this as when he started to understand when to invert. He said, okay, how do I keep the pilots safe? And he's like, there's a lot of answers. There's a lot of things pilots are doing. So he actually flipped it. He inverted it. How do I kill the pilots? And once you understand how to kill the pilots, you understand the most important things that you need to communicate to the pilots to keep them safe. Okay. And so what he concluded was actually there were 2 main ways that you could kill pilots. One is by not telling them when they're going to get ice on their wings. Okay. So ice on the wings, conditions that where you're going to get ice on the wings, critical to get out to the pilots. And then the other thing was fog, you know, when they couldn't see. And so forecasting fog, critically important. So he moved those, and it wasn't just, you know, he prioritized getting that information to the pilots because human nature, right? If you bury the headline, if you put the most important things down deep, then people might not pay attention to it. But when you put the 2 most important things up top, they see it and they know have the information they need to you know, basically make it back to the airport safely. Okay. So I favor unfavorable conditions here. Okay. Where does ISCO have unfavorable conditions? First of all, it's been a very successful technology for 25 years, but that doesn't mean it doesn't. There are compounds it doesn't react with, but there's a lot that it does, okay? Unfavorable conditions, though, a lot of it gets down to dosage. You can, and people do, underdose ISCO all the time. One of the things, high concentrations, okay? You're limited by what you can get into the ground. You know, 5%, that means that you can only treat X amount of contamination. They're around 10,000 milligrams per kilogram in a single application of, you know, like different contaminants, okay? Low contaminant concentrations, believe it or not, these are hard, okay? And it's because of establishing contact. And the analogy I like is fish in a lake, okay? If your lake has an abundant level of fish, say 100,000 fish, you can cast out in the lake and it's going to be pretty easy to catch a fish, okay? If you have a single fish in a large lake, you can sit there and cast on something again and again and again and again, and you might not even be in close proximity to that fish. Low levels of contamination are the same thing. You know, if you have a part per billion, establishing contact with that part per billion is hard. The way to compensate for it is having a lot of casts and working the lake or having a lot of anglers. And that means overcompensating for the lack of contamination by having more than you would think of ISCO. And this is a common pitfall I see people make. They go out there, it's like, well, I have 1 part per billion, so I only need, a few parts per billion of ISCO. That's wrong. You're not going to have success. Okay. And I actually have instituted a number of different minimums. If you guys work with us, I have minimum dosages. And that's one of the ways I get around this. It's like, I don't care if their math says that they don't need it. Tell me how that they're going to establish contact with 1 part per billion and we can talk. And what I compensate is hitting it with more ISCO. So that's another failure, but you can underdose even low concentrations. High non-target demand. So the whole SOD thing evolved out of failure. This was an unfavorable condition. This was Cape Canaveral. They went out there and they were applying permanganate and they injected it. These scientists, that was professors, they went out there, figured everything out, had it down, never saw permanganate out of injection well. It's purple. It's hard to miss. So they went back and they figured out why they missed it. And they hadn't taken into consideration the target demand associated with soil. And that's where soil oxidant demand, the test was born. Okay, it was born out of failure. Establishing contact, this all for different reasons. NAPL, high concentration, but also if you think about it, we need stuff in the aqueous phase. And it has a low surface area, high volume ratio, difficult to establish contact, extreme concentrations, low KOC, high KOC, low solubility contaminants. If they don't come off the soil, we can't establish contact. Okay. And so some things are desorption limited, diffusion limited. Rapid groundwater velocities. Again, some things need contact time, okay? And so those things can be issues. So sufficient quantity, and it goes back to the thing, establish contact, sufficient quantities, long enough time, and we need to have those things in order to have success. And of course, there are a few compounds that we don't work with. We can treat the carboxylic acids, but not the sulfonic acids, PFOS, some pesticides. We don't have very good reactivities with those compounds. So you flip this around. Now that we understand what to avoid, and this is why I have the list, the bullet list, the 5 things I do. Can we establish contact? Yes. Can we establish sufficient contact between the oxidant and contaminant? Yes, these are the favorable conditions. Remediation time frame matches the oxidant? Yes. Contaminant demand can be met with a reasonable number of applications. Again, there's another yes for you. And then other technologies are not more cost effective. Yes, we've avoided the pitfalls of ISCO. Therefore, these are the favorable conditions. And Charlie Munger smiles at your side. Okay, data needs before, during, and after. Okay, so I want to know everything. I don't think that's an unfair request. I want to know soil type. I want to know heterogeneity between the soil types. I want to know water content. Some people forget vadose zones don't have as much water as saturated zones. And vadose zones can vary. If you have a vadose zone and it's in a park, what rain gets into it, it's going to have water. Surprisingly, amount of water sometimes. I mean, if you look at the specific yield, clays can hold 92% of their porosity, okay? Sands can hold 72%. But if you're underneath a concrete slab at an industrial facility where rain can't get to it, it could be 0, okay? So you got to pay attention to even water content. Key parameters: soil bulk density, hydraulic conductivity, porosity, effective porosity, fraction of organic carbon. I've been telling you how much I'm worried about sorption. Fraction of organic carbon is the #1 mechanism that contaminants sorb to soil. That's why Alana was talking about adding carbon. It's just like if a site doesn't have enough, we'll add a little bit more. Groundwater velocity and flux. These sites are not static, they're dynamic. We need to understand the ways that they're dynamic. So what's the groundwater velocity and flux look like? Are there preferential flow paths? And there's always preferential flow paths. Contaminant distribution, where is it located? How did it get there? Contaminant types, phase, and concentrations. And contaminants are commonly treated in source areas, secondary source areas, which is a fun concept, and plumes and property boundaries and fractured bedrocks. But again, and I try to emphasize things I want you to think about. This is one of the things I want you to think about. Paul and I yesterday were calling them our soapbox. It's me up on a soapbox. Assumptions are bad. Why are assumptions bad? Okay. If you make an assumption, if you tell me to assume my reagent distribution, my injection volumes, my injection rates, the groundwater velocity, just assume it's sand. Okay, the hydraulic conductivity of sand. Well, sand has a 5 order of magnitude range of hydraulic conductivities. Okay. Gravels have a 3 order, these are typical, this is taken out of my hydrogeo book. Gravels have a 3 order of magnitude range. Silts have a 2. Clays even have a 3 order of magnitude range. It really is good to be working with actual site data. Let's make sure that we are collecting this information so that we're not making assumptions. And so this helps talk about the dynamisms, this helps talk about can we inject and all these things. But let's talk about just basically how an assumption can impact whether or not you're making a good estimate as to how much oxidant you have out there, because underdosing can happen. You derive an oxidant dose by knowing how much contaminant mass, making estimates of the contaminant mass. You have you need X amount of contaminant. If you have X amount of contaminant, you need Y amount of oxidant. Well, the way you estimate your mass, most of it is typically on soil. So you figure out your contaminant concentration, X milligrams per kilogram. But then you multiply that X milligrams per kilogram times the density of the soil. So let's talk about the range of soil bulk densities. If you have a sand, there is a 50% range variability in the assumptions that you can make on the density of sand. Clays, there's a 60% range. The bottom line is, and this is a simple parameter to get, site-specific parameter, let's get these things. It's always best to have site-specific data to understand the variabilities of each site. Monitoring program, questions are important. Ask good questions. Get good answers. Do not have a clue what question you're asking, you may not get the answer that you want. Whenever I was writing a work plan, back when I was practicing doing actual work, I would actually, one of my sections, my lead sections would be like, these are the things we're trying to accomplish. Okay, this pilot test is trying to accomplish X, Y, and Z. This monitoring program is trying to accomplish X, Y, and Z. It's very critical. So in the terms of a monitoring program, before, during, and after, again, we like information, but generally speaking, you of course want to know what's going on with the contaminants. I will say when something goes wrong, I don't look at the contaminant concentrations first. I actually look at these secondary parameters first, because if you don't get distribution of your reagent, if your reagent does not contact your contaminant, you should not even expect treatment. So I look at things like conductivity. That tells, there's so much salt in these things, it tells you where things were distributed. Persulfate, that tells you if you have something active persulfate or permanganate or ozone or hydrogen peroxide there. Sulfate is a good secondary indicator. Electrical conductivity is a good secondary indicator. Sodium, potassium, whatever the active ions are that are associated with your residuals, tell you where your reagents went. Okay. One of the other things, just real quick, dissolved organic carbon. People don't appreciate the fact that ISCO actually usually stimulates bioremediation. People, you don't sterilize the site. I'm not aware of that happening. What actually usually happens is that you partially oxidize the native organics. Those native organics go into the aqueous state, become DOC. So you tend to see a spike in DOC. That spike in DOC, that's bug food. So microbial populations usually suffer a little bit during ISCO, and then they rebound as that DOC. I've actually seen estimates where as much as 30 to 40% of the total destruction was actually from bioremediation after an ISCO application. So just one of those things that if you don't monitor for it, you will never see. Proper monitoring, and there's just a lot of detail. Monitoring programs that could be talking about for hours. We actually have webinars on it. I have a presentation that I go around and make. But you monitor for a lot of different things, but it's amazing the things with a well-constructed monitoring program you can get good information on. Reagent distribution, very important. Reagent longevity, very important. Where, what pathways did reagents go through? Very important. Was something recontaminated or rebound? Recontamination coming in from upgraded, rebound from, like a NAPL or a low perm zone inside it. You can actually design a monitoring program to help you answer all these, but this is generally the data that you need to do most of those. Implementation logistics, no one thing that we do is very hard. What is hard is getting all of these 800 things that we need to do to implement things to be done properly and in correct sequence. Said a very, 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 very wise man, good looking and charming too. Yes, this is what I used to tell my field crews going out to work, okay? there's a lot of stuff that we need to do. I'm running out of time, so I'm going to skip through it. But I do want to emphasize the devil is in the detail, okay? It is important to pay attention to each thing. A quick example would be, like we can make all these cross sections that we want and know where the contaminants are, but if there's variability along the surface of where you're putting wells, and you don't take that into account, your injection wells, your monitoring wells are not going to be where they need to be vertically. I do also want to emphasize path to a typical ISCO project. I do like bench tests, if nothing else, for design parameters. Technical efficacy, every now and again, we do see interferences. Pilots, I like pilot tests a lot. And you can use them to not only confirm technical efficacy, but look at distribution, look at establishing contact. Chemical compatibility are the big lessons learned. You can see corrosion here, you can see corrosion here. You can get around corrosion of carbon steel by adding an alkalinity. A lot of other lessons learned, and I'm running out of time, so I'm going to just move along. One of my big lessons learned is that everything is related, and that's actually one of the overall mechanism things I'm trying to talk about here. Chemistry, application method, monitoring, site characterization. We have a lot of tools in the toolbox, and this is how you figure out by looking at everything holistically, which one to use. And then there's a stepwise process, site characteristics. You look at the site, you look at the contaminant, you look at the ISCO characteristics, select the application monitoring, develop your monitoring program. And then these are the best practices. Understand your site, chemistry, design, application, and you will probably have good luck. So sorry, I go down the rabbit hole.